So today we're talking about tensor products, or generally tensors. What are they? And when physicists hear the word tensor, they immediately think of tensor fields and like all that Riemannian geometry stuff. But we're actually not doing that. We're just doing the algebraic theory behind it with some functional analysis at the end to look at the tensor products that we use in quantum mechanics, because there's, I guess, nice results there. And yeah, this is also a topic that has always been avoided, which sort of gave birth to the whole idea of forbidden maths. So now finally we get to do it. And well, they have always been alluded to, and people might ask, well, what actually is a tensor product, or what are tensors? And in my opinion, that's not the best question you should ask. The best question is, how do I work with them? So sort of the synthetic approach versus the analytic approach. And well, one thing we could characterize them is sort of categorically by means of the so-called tensor home adjunction, which means that linear maps from U tensor V to W, that this is supposed to be isomorphic to the space of linear maps from U to the linear maps from V to W. Or what this is bilinear maps from U cross V to W. And well, to be fair, this is again not really something we should use as a definition, because this is sort of a result that, oh nice, vector spaces are a monoidal closed category, but still that is one way we can approach them. So yeah, the another way to phrase this is that the tensor product of two vector spaces U and V satisfies a so-called universal property. Well, U and V are also vector spaces. Namely, if we have any bilinear map from U cross V to another vector space W, then there is a unique, then there is a unique map. This way you write this, right? Exists a unique map from U tensor V to W, such that this bilinear map factors through the sort of canonical map from U times V to U tensor V. And this sort of is a universal property because, well, it's sort of phrased generally, and because it characterizes U tensor V uniquely. And well, in a way, this is all we need to work with tensors, because, well, what do I mean by working with tensors? It means that we have a way of mapping from this tensor product space and a way of mapping into that tensor product space. And the way of mapping into that tensor product space is this linear map here. And the unique way of, or the way of mapping out of it is by means of this universal property. But of course, I agree that that's not very helpful. I mean, it's a vector space. At least it's supposed to be a vector space. So we should be able to say more about it than just, oh, we have some abstract concept of mapping into it and mapping out of it. And more importantly, we are saying that this property sort of characterizes the tensor product uniquely, but does it even exist? I mean, this is only the uniqueness part of everything. And well, I guess it's a short lemma that it does indeed exist, namely let U and V be finite dimensional vector spaces. Then, yeah, we take the space of bilinear maps from U and V to K, and we take its dual, and this one is a tensor product of the two. I don't know, the proof is rather boring. I don't know, would you like to see it or not?
Maybe a short sketch.
A short sketch. So, well, what do we need to define? We need to define a map from U cross V into that space. So cross V into that space. And this one should be bilinear. And what does this map do? Well, pair UV is mapped to, well, some map that takes. Ah, Srinivas, hey.
Yeah, sorry, dude, I was in a meeting, so I just got late.
Ah, okay. Yeah, I just introduced tensor, the tensor product of two vector spaces U and V as sort of the unique vector space such that any bilinear map defined on U and V maps through that one. And then immediately conceded that this isn't very helpful yet. But well, now as a first result, I'm saying that at least for finite dimensional vector spaces, such a tensor product at least always exists. And well, what happens afterwards, we shall see. And yeah, since this tensor product is supposed to come with a bilinear map from U and V into it, this is the map I'm defining right now. So I'm taking a tuple U and V of vectors inside U cross V. And I'm mapping this to a linear form on that space of bilinear things. And what does it do? Well, it takes a bilinear map and maps it to L evaluated and U and V. And yeah, that sorry, this is obviously bilinear because this L is bilinear and blah, blah, blah. At some point, we have to use that. We're working with finite dimensional vector spaces, but then we see that this indeed satisfies the universal property. Yeah, for infinite dimensional vector spaces, we would have to use a slightly more involved construction. This is, I mean, the tensor product is also defined for general modules, and this construction always works. So you have to do some stuff with free module and then tensoring out a whole lot of stuff, basically giving you what you want. Yeah, it's not very instructive. So the next question we can ask ourselves is, so, okay, we've shown that these tensor products exist for finite dimensional vector spaces, but do we actually get some information about the basis of that vector space, for example? Or what about the dimension? yeah, and from now on, I'm not going to suppose a particular model for that tensor space and just call it U tensor V and write small u tensor small v for the image of uv under this map here. Well, if we're talking about finite dimensional vector spaces, because for infinite dimensional vector spaces, that dimension would just be infinite. Well, we have U tensor V is isomorphic to, like I just said, that space of bilinear functions from U and V to K dual. But again, since finite dimensional, that one is isomorphic to that space of bilinear function. So, well, we need to count bilinear forms, essentially. So now, yeah, I guess choose a basis. And Vi of capital V, the bases, then define phi. And yes, you can already see it, a lot of indices here. I mean, this is sort of why we have the Einstein summation convention, right? But I'm not going to use that one quite yet.
Thanks.
And yeah, well, we can now just define bilinear forms phi ij by applying them to basis vectors and just saying that this should be Kronecker delta ik, Kronecker delta jl, meaning that, well, phi ij ui vj is 1 and everything else is 0. So if you want to write it in terms of matrices, it's just a matrix that is 1 in one, that has 1 as one component and 0 everywhere else. Yeah. Well, I mean, you can see that you can choose n different values for I and m different values for j. So those are n times m different objects, I guess. And well, in a way, we can decompose everything in terms of these just by saying that if we have another bilinear form, then we can write this thing as, well, we can insert a couple of Kronecker deltas, just cos j from 1 to m, delta ik, delta jl, psi ui vj. Okay. Then we notice that this combination here is what we defined our phi ij as. So that is phi ij uk vl psi of ui vj. And we see that the things we put in here are now here. So that, well, conclusion by bilinearity, we can write psi as this sum psi ui vj phi ij. And this is unique. So the phi ij are the basis of the bilinear forms on uv. And then we can take the dual basis and we sort of get a and then we sort of get the basis for the tensor product.
In this case, when you're taking the dual basis, by the way, I could hear a reverb. Is there some, I don't know.
I mean, it's raining here, but
Okay. No, so when you're constructing the dual basis here, would you say they would then just be like some sort of outer product of these vectors?
The dual basis would then be psi ij of phi kl defined as delta ik delta jl essentially,
Okay.
which happens to be phi kl of ui vj, meaning that this is, yeah, if we sort of look at what I defined up here, that psi ij is the map that takes a bilinear map and inserts ui vj into it.
Okay. Yeah.
So that is, well, exactly that thing here.
Yeah. Yeah.
So that gives us sort of the result that we all knew, all thought we already knew, that if you take a tensor product, then the basis, or then a basis for that tensor product space is just given by the product basis of two bases for the vector spaces. And yeah, this then shows that the dimension of U tensor V is the dimension of U times the dimension of V, meaning that the tensor product is, or let's say if the direct sum of vector spaces is the sum, and the tensor product of vector spaces is a product, whatever that means, but yeah. Yeah, next thing. In the category of what can we do with tensor product spaces, we're looking at tensor products of linear maps. Essentially, well, how can we define, or what special cases for these bilinear maps that we have, or can we define such that we get maps on the tensor product space? So let U, V, W, and X be vector spaces. Phi be a linear map from U to W, psi be a linear map from V to X. Linear. Then the map that maps U and V and U cross V to phi U tensor psi V is bilinear, just by virtue of this thing being linear, this thing being linear, and the tensor product being bilinear. Yeah, this thing maps from U times V to W tensor X. So we have a bilinear map, and by the universal property, this now induces a linear map from U tensor V to W tensor X, right? And what does this thing do? Well, it sends an elementary tensor to phi of U tensor psi of V. And this is usually how we write that construction. So we don't always have to go through bilinear map and then blah, blah, blah induces. No, we just say what it does on an elementary tensor and then continue by linearly. So form the linear continuation or something. And well, this is a special map because it's induced by phi and psi. So we give it a special name. And yes, I know I'm straining the symbol, but call it phi tensor psi. Okay, for some reason I made a typo. Never mind. And yeah, when we are dealing with linear vectors or with finite dimensional vector spaces, well, taking the tensor product of two linear maps is again a bilinear operation, right? So it again induces a map from linear maps from U to W, tensor linear maps from V to X, to linear maps from U tensor V to W tensor X. And well, by a dimension argument for finite dimensional vector spaces, this thing is an isomorphism, meaning that, yeah, we can write any linear map between tensor product spaces in terms of tensor products of linear maps. But maybe we want to write it as a matrix. So, I mean, at least some of us are physicists, right? Linear maps are the same as matrices, so we have to know how to calculate with them. What does it look like as a matrix? It referring to the map phi tensor psi, given the matrices for the maps phi and psi. Yeah, I guess we again choose bases. Ui, Vi, Wi, Xi. Bases of U, V, W, and X. And let phi of Ui be the sum of phi ij, Vj. So yeah, basically write this linear map in terms of indices. That one too. And then, well, by definition, phi tensor psi applied to Ui tensor Vj, one of our basis elements of the product basis, is equal to phi of Ui tensor psi of Vj And now this is equal to IR psi JS WR tensor XS. And if we now count, or if we order our product bases sort of with lexicographically, so we have U1 tensor V1, then U1 tensor V2, and so on. Then U2 tensor V1, U2 tensor V2, and so on. Then we have, well, UI Vj is mapped to phi 1, 1, W1 tensor, and then we have psi I1 X1 plus psi I2 X2, and so on. And we have, yeah, I think there should be a, okay. Yeah, I wrote it weirdly. U1 tensor Vi is mapped to that. And then we again have psi 1, psi I1 X1, psi I2 X2, and so on. So we basically have the same thing here always, and this thing here changes. So if we, yeah, I don't really know how to phrase this, but essentially we get a copy for the matrix of psi at each entry of the matrix for phi. In easy examples, if this is the matrix for phi, and this is the matrix for psi, you get as a result a 4x4 matrix, namely the one having a copy of the second one at each entry of the first one. And I mean, of course, you can write this one out, but it's rather dull. One example of this would be, for example, if we take the matrix 1, diagonal matrix 1 minus 1, and the diagonal matrix 1, 1, we get 1, 1, minus 1, minus 1. Sorry, it must be a tensor product here. So this is sigma 3 tensor identity matrix. This is I sigma 2 tensor sigma 1. Yeah, and so on. So I don't know, just the Dirac gamma matrices. You can write them as tensor products of Pauli matrices. That's what I was trying to say. Yeah, somewhat different way of looking at it, at the whole tensor product business, is, well, essentially every vector space is just our base field to the nth power, or to any power. So we can just start from there. then we can interpret that space of bilinear maps just as the space of n times n matrices, because essentially every such map can be written in the form of, well, I have a column vector, can transpose that, get a row vector, multiply it with a matrix, multiply it with the other vector. And that matrix then happens to be n times m, I think. So we can just make this isomorphism there. So then Kn tensor Km is isomorphic to nm matrices, well, the dual space of them, but the dual space of the n times m matrices are the m times n matrices. And that's it. This thing via the matrix B, and I send this to the map that sends A to the trace of A times B, because the trace more or less describes an inner product, or let's say the trace of A times B transpose describes an inner product of the space of any kind of matrices. And then when I don't take the transpose, I'm sort of reversing the order of the, taking the transpose outside. So what does this thing look like? Well, we send U tensor V to the map that sends A to U transpose AV. But we can write this thing as the trace of, well, itself, because it's just a 1 times 1 matrix. Then we can use this cyclic property of the trace to pull the V in front. And then under this isomorphism, this then gets mapped to V times U transpose. So in a way, we can view the tensor product of an n-dimensional vector space and an m-dimensional vector space as matrices whose that are have m rows and n columns, and then view the tensor product operation just as the one that takes the transpose of one vector, multiplies it with the other to give such a matrix. This might also be familiar to the physicists who were first introduced as, yeah, tensors, at least two tensors are just matrices. Well, in this sense, they are just matrices. And, okay, next thing. I wanted to talk about is, again, go a bit back to that isomorphism here and see what other nice things it gives us. So yeah, for finite dimensional vector spaces, we have that this tensor product X, Jesus, UW. This thing is isomorphic to the linear maps from U tensor V to W tensor X. example, or I guess special case, we can just let u and x be equal to k. Then we have u tensor v is equal to, well, it's the same as k tensor v, which is isomorphic to v. Similarly, w tensor x is isomorphic to w. So this gives us that the linear maps from v to w are given by linear maps from k to w tensor linear maps from v to k. But like linear maps from like the real numbers to a vector space is just given by a vector. Similarly for any other field we put in here. So that's just w itself. And this thing here is nothing but the dual space. So linear maps from v to w are isomorphic to v prime tensor w. This would be the basis-independent version of the idea that the tensor product is just matrices. Well, matrices are just the tensor product, but you have to take the transpose of the first space, which, I mean, sure, here, transpose. And in particular, what is if v and w are the same? Then end v is the same as v prime tensor v. But now we have a finite dimensional vector space. So v is the same as vw prime. Then we can turn it around. Then we can sort of apply another special case, pull a prime out, and thus get that the endomorphisms are their own dual space, which again, I mean, I've already shown an inner product on that space. So that shouldn't really come as a surprise.
What are these primes exactly? I once again heard the reverb. I don't know why that's happening. Every time I talk, I hear myself.
Huh, weird. Prime just means dual space. So v prime is the linear maps from v
No, I get it.
into k. So do I have anything else? Okay. So I don't know, this now was a lot about tensor products of two spaces, but in physics, we are rarely content with just tensoring two things. So are there higher tensor powers? And yeah, I guess one question might be, is the tensor product associative? Meaning, is this thing at least isomorphic, naturally isomorphic to this thing? It takes a bit of diagram chasing, but that is indeed the case. So nothing prevents us from defining sort of recursively the tensor powers of a vector space V, namely by saying that the zeroth tensor power is just the underlying field. and the kth tensor power is just v tensored with the k minus first tensor power. So no surprises there, I suppose. And yeah, in physics, we usually want to take negative tensor powers in quotes, or like want the distinction between contravariant and covariant indices, or generally covariant and contravariant tensors. So we define a slight generalization of this, namely the pqth tensor power of V. Define it as the pth tensor power of V tensored with the qth tensor power of V prime. Or alternatively, as the qth tensor power, I mean, this is isomorphic to the qth tensor power primed tensor, well, the pth tensor power of V. And now this is by the universal property there's a whole lot I didn't mention here, but law. So this is now somehow isomorphic to the linear maps from the qth tensor. Yeah, of course. We have here something of the form, we take a vector space, take its dual, and then tensor it with another vector space. So we've just shown that this is isomorphic to tensor power, this is isomorphic to the linear maps from this vector space to that vector space. So that thing. Just because when we prime this thing, we get this, and then we tensor with the other thing. But now by the universal property, this is isomorphic to multilinear maps from V from Q copies of V to the pth tensor power of V, which is sort of one way in which we usually characterize these tensors. Another thing might be as a multilinear map that takes Q copies of V and P copies of V prime and maps them all to K. That is sort of the analytic definition usually used for these tensor powers, but I mean, it's all isomorphic. It's all uniquely and naturally isomorphic. So
yeah, just one question I'd like to ask here is there some issue with the ordering here when we are doing all these processes? Like, because I don't assume it's a commutative product, right?
yeah, well, what you mean by commutative? So the tensor product, so if you take the tensor space of, or the tensor product of V with itself, and then you have elements U and V, then U tensor V is very much not the same as V tensor U, except when they are linearly dependent, or like when they are basically the same. But the thing is, if you discuss vector spaces, then this thing is isomorphic to W tensor V, just by
I see.
mapping this elementary tensor to that one.
Okay. So it's isomorphic, but it's not the same thing.
I mean, in category theory, there's not really a difference, but it's as vector spaces, they are sort of very much the same. Within one of those spaces, when both of these things make sense, then they are different. Does that answer your question?
Yeah, it does. But we can basically say that even in this case, U tensor V, like the basis vector is tensored, we can say that there exists an isomorphic map from U tensor V to V tensor U.
Well, there's a map that maps one to the other.
Yeah.
Namely just the one that we define to be that way,
Yeah.
incidentally.
Yeah. And that should be an isomorphic map, so it's fine.
Yeah, sure.
Yeah.
I mean, there's always an isomorphism which maps one to the other, but I mean, the same can be said about the complex numbers. If you view them as a group or something, then you always find a group homomorphism that maps one to the other, if they're both non-zero at least. Yeah, and maybe something more relevant, because I mean, this is something that's used in like differential geometry, maybe Riemannian geometry a bit more, GR, okay. But the one thing I want to work towards is the tensor algebra. And for that, we just consider again just our plain old tensor powers here. I guess we could call them T0V and TKV, just by omitting this lower index and saying that it's supposed to be 0. And then we can collect the positive powers. And we define the tensor algebra of the vector space V to be the direct sum of T and V. So what is this? Well, this is K direct sum, V direct sum, V tensored with itself, direct sum, V tensored with itself 3 times, and so on. So what we have, the elements of TV are just polynomials in elements of V, except that nothing commutes. So TV is now a non-commutative graded K algebra. I mean, it is commutative when your vector space is one-dimensional or zero-dimensional, but I mean, that's only very rarely the case, so it's usually non-commutative. Well, how do I describe, or what is the product? So the product is just the tensor product. And it's graded because, well, it sends a monomial of n elementary it sends a monomial consisting of n things and a monomial consisting of m things to a monomial consisting of n plus m things. So U1 tensor until UN, V1 tensor until VM is just sent to U1 tensor until the UN times V1 VM. So in a way, like the polynomial ring would be the most general commutative ring that contains both K and that vector space. The tensor algebra is the most general non-commutative ring that contains both K and that vector space. So everything we've ever wanted to construct out of every ring we've ever wanted to construct out of vector spaces, we can somehow realize using this tensor algebra, and then maybe quotienting out an ideal or two. So let's do that then.
What do you exactly mean by graded here? I'm slightly confused.
Graded just means that we can write our space as the direct sum of subspaces.
Okay. Yeah.
And the subspaces, although the product has this nice rule that it sends elements of degree n and elements of degree m to elements of degree n plus m. So the degree is sort of additive.
Okay. Yep.
And yeah, so now we have a bunch of examples. So first example would be what I already mentioned, what I'm now calling the symmetric algebra, which is just the tensor algebra quotiented by the two-sided ideal uv minus vu, where u and v are in v, meaning that, well, those expressions are all 0. So product is now commutative, and we have just a ring, a commutative ring. So this is also the same as K adjoint V, I guess. Note that this thing is a homogeneous ideal. So it is generated by objects that have sort of homogeneous degree. This thing has degree 2. This thing also has degree 2. So this thing is a homogeneous element, and the ideal is then generated by these homogeneous elements. So it's a homogeneous ideal. And when we quotient by a homogeneous ideal, we still get a graded algebra. And I mean, yeah, sure, we can just grade polynomials by their degree. It's the same thing. And yeah, I guess we have a natural isomorphism between the nth symmetric power of V prime and symmetric and multilinear forms on V. Then the dual of that, wait, it can't be true. Should be like that, I think. So the symmetric powers, or the symmetric algebra, whatever, is related to symmetric multilinear forms. That's just it. So second thing, the exterior algebra, written hilariously as lambda capital V, which is, well, a very similar thing, but we quotient out by the ideal where we have a plus here. Oh yeah, here we usually write.
Wait, by the exterior algebra, do you mean this is like the exterior product, like the wedge product?
It is alternating. So that is sort of the universal property for the exterior algebra. I mean, we've defined like omega n as for a manifold as sections of the bundle that is defined as the exterior bundle of the tangent bundle, where that would just be the exterior power of the tangent space and so on. So it more or less is in sync with what we've done before.
So this would be the anti-symmetric and multilinear forms.
Yeah. yeah, something I quickly wanted to mention, when we're going from the tensor algebra to the symmetric algebra, we use a slightly different symbol for the product, and we use this symbol there. Same as for function composition, which is weird because suddenly it's commutative, but okay. For the product. And here we have, well, this thing, this is again a homogeneous ideal. So lambda v is graded, and we usually write the product as wedge. And wedge is antisymmetric or alternating. Meaning that U product V is equal to -1 to the degree of U times the degree of V. V times U for homogeneous elements. And yeah, this is exterior algebra of V. And yeah, we have a natural isomorphism between lambda of V prime and alternating multilinear forms. And generally, if we have any of those constructions, they are functorial in V, because we can sort of in a natural way continue every linear map that maps into a, yeah, we can continue any linear map on V, or like on any kinds of vector spaces to the tensor algebra. So then we can also apply them to vector bundles if we want. The symmetric power isn't that much used, although you could argue that metrics are sections of the symmetric second power of the cotangent bundle. And similarly, for the exterior thing, like n forms are sections of the nth exterior power of the cotangent bundle. Yeah, the constructions that we can actually transport to manifolds doesn't really stop here. Next thing, if
So is this the formal definition for the nth exterior power, or
yeah,
okay, or is it just like it has a different formal definition and these are just equivalent?
no, I mean, this is usually what is taken as the formal definition of the exterior algebra.
Okay, okay.
And then from there you can define, yeah, exterior powers
Products.
of vector bundles, and then define differential forms based on that. And all of the alternative characterizations for differential forms, like, oh, it takes n vector fields multilinearly and alternatingly and sends them to a smooth function. That's just a, well, basically it's just index stuff.
Yeah, yeah.
So yeah, next construction that we also did for a bit in topology and physics. Let's Q be a quadratic form. On V, meaning that it is the map sending V to beta of VV for some bilinear form V. We can define Clifford algebra VQ to be, well, again, the tensor algebra divided by an ideal, and which one? Well, U times U minus Q of U for all U and V. Meaning that we basically say that the element U should square to Q of U, which is a number of an element of the underlying field. Now, notice that this thing here, this element here is not homogeneous because this thing is degree 2, this thing here is degree 0. So Clifford algebra, sadly, is not Z-graded. But
I'm very confused. How do you divide by this? Like I don't understand. Like
well,
I understand it's not Z graded as a result, but like what does division by this ideal even mean? Like
it means that you set everything as in this ideal equal to 0.
No, but how do you equate something that is degree 2 to something that is degree 0?
Well, you just say it should be, and then you can't talk about degrees anymore, but like you still have a vector space. It's just that talking about degrees doesn't make any sense anymore, but that shouldn't necessarily be the case.
Like what is the structure? Like if it is not Z graded, like how do you even visualize it? Like how do you?
Well, it's still a vector space. That vector space is usually quite finite dimensional. In fact, usually, or not always, if V is n-dimensional, then the Clifford algebra is 2 to the n-dimensional. You can still write down a basis by fixing a basis of V and then taking sort of monomials that have increasing indices. So you can still perfectly well just view it as a vector space. Or I mean, even as an algebra, because like you still have that product.
You can continue. I will try to understand like while you're speaking. Like you can continue the.
Okay. So this thing is not that graded, but notice that, well, we still have a sort of residual grading left, because this thing has an even degree and this thing also has an even degree. So we don't have a degree of like 0, 1, 2, 3, but we still have the distinction between even and odd elements. And yeah, that's all that's left. But still Z2 graded. Or I mean, if you want, no, sorry. If you wanted, you could also call it supercommutative, but that's not even true. Only if Q is equal to 0, then it's supercommutative. Maybe. Yeah, so that means split in odd even. Yeah, this thing is called the Clifford algebra. And yeah, I mean, the elements are given as tensor powers or tensor products of elements of V, with the condition that if you square something, you get Q of that thing. At least when you square a vector. Anything else is a bit more involved. And lastly, the last construction that is missing. Oh yeah, but by the way, what I've just said, you can take the Clifford bundle of TM G with a metric G, then that thing is a bundle of Clifford algebras, yeah, on pseudo-Riemannian manifolds. But just as a side mark.
What's the relation between G and Q exactly?
So if G is a metric, then you basically define Q of some section S to be G of S with S.
Okay, okay.
So basically the square with respect to that.
The diagonal elements, basically.
Sorry?
Like the diagonal elements.
Well, yeah, in a way. Yeah, and last construction. And we all know what's coming. If G is a Lie algebra with Lie brackets, then we define the universal enveloping algebra. Full circle, right? As the tensor algebra, where we divide out another ideal, namely U tensor V minus V tensor U minus bracket of U and V.
Yeah, I have one important question here, especially here. Why is this a Poisson algebra?
Well, if you now take, well, basically because it's, okay. So now on this thing, you can also sort of continue your bracket just by saying that U times V W, that this thing should be U VW plus UWV by definition. No, I mean, you can also just take this thing as the commutator, and then it's a Poisson algebra because it's the commutator. I mean, that always holds true.
I'm confused. Like, you have these U tensor V minus V tensor U minus the Lie bracket.
Yeah.
And for some reason, this is a Poisson algebra structure.
Yeah. So the thing is, this just means that the commutator, in the sense that you would define it for an algebra, is the same as the Lie bracket.
Lie bracket, yeah.
Yeah. And then, well, if you want to define a Lie bracket on this thing, you just take the commutator, because you know, if you plug in actual vectors that are in the Lie algebra, then I'm going to get the Lie bracket. So I'm not losing any information by doing that.
Yeah.
But then it's a Poisson algebra just because, well, any algebra equipped with the commutator is a Poisson algebra. Because you always have UVW, well, that's the same as UVW minus WUV. And then, oh no, if I'm doing this correctly, minus VUW plus VUW minus WUV. Huh. Okay, bad.
But in some iteration, it should work out basically. It should
Yeah,
become 0 basically.
well, not 0, but like whatever, but like this thing here.
Yeah, I'm sorry for asking this question, but I just wanted to like clarify this once. Like,
well, yeah, I mean, it's just because in the end you define your Poisson bracket as the commutator, and we have already verified that it always holds that construction always gives us a Poisson algebra structure.
okay.
Yeah, so universal enveloping algebra. So now is when the fun starts. Because I mean, until now we've mostly talked about finite dimensional vector spaces, just because in physics we usually don't talk about bases in the way that we talk about them in maths, because in maths we always want finite linear combinations because we don't have any topology. But in physics we are usually working with Hilbert spaces, so we don't use Hamel bases, but like Hilbert space bases or Schauder bases or something like that. So how does this tensor product stuff behave when we, instead of looking at just algebraic vector spaces, when we look at Hilbert spaces? I mean, during the operator theory lectures, I already introduced the tensor product of Hilbert spaces, but do we also have a universal property for those? So first observation, multilinear maps are a bit harder. I mean, we've started by talking about multilinear maps, but what does it actually mean for a multilinear map to be bounded or continuous or something? And yeah, generally they are a bit harder in Hilbert spaces, especially in light of the fact that we want a trace from H tensor, H dual to C. Yeah, of course. So, I mean, this thing sort of classically for finite dimensional vector spaces would just be the endomorphisms of H. And we have a trace on there. And we sort of also want to have a trace for operators on the Hilbert space. But the thing is, like, most operators don't have a trace. Definition, an operator on H, it's bounded, is called trace class. If it has a trace. Huh. So, okay. So what does that mean? i.e. for any or equivalently every orthonormal basis vi I in some index set of H, we have that the sum over these norms is finite. Yeah. Denote the set of all trace class operators by B1 of H. Sort of usually we also call bounded operators B of H. Then those would be B1 of H. Why the 1? Well, because we'll soon see that there's also a B2H. And then define what we actually wanted to have, namely the trace from B1H to the complex numbers by sending an operator to that sum here, VI, AVI. So that's basically the basis independent way of summing all of the diagonal elements. And this condition here just means that the sum even converges. And yeah, I guess we get similar results to linear algebra. So B1 of H is a Banach space. When equipped with the norm that sends A to the trace of the absolute value of A, where the absolute value of A is just the square root of A dagger A. And second important observation, B1H is an ideal of LH. Basically, if we multiply by a bounded operator on the left or on the right, we still get something trace class, which basically comes back to the fact that this thing here or this thing here just says that the eigenvalues some sort of form a sequence that is summable. So the eigenvalues lie in small L1. And we can multiply an element of L1 by a bounded sequence and still get an element of L1. Now that's also where this one here comes from. Yeah, I guess that's also the remark I have here afterwards. So those are exactly the operators for which firstly the spectrum is discrete, and secondly the eigenvalues, if we sort of take the sequence of all eigenvalues with multiplicities, then they all sum to something finite in an unconditional way. And what's perhaps more important, sort of, this is a Banach space. This is sort of equivalent to L1, but we actually want L2, so some kind of Hilbert space. And this is what we define now. Operator on H is called Hilbert-Schmidt. If A dagger A is trace class. When we denote the space of Hilbert-Schmidt operators by B2. And we can give this space a sesquilinear form. B2H equipped with the operator, with the bilinear map, sesquilinear map that sends A and B to the trace of A dagger B. is a Hilbert space. Who would have thought? Again, similarly to square matrices that also form a Hilbert space with this inner product. And now to generalize from Hilbert-Schmidt to somehow get to bilinear forms. A bilinear map L from H1 cross H2 to H is called weakly Hilbert-Schmidt. And now it becomes a bit tiresome if there is a D and R such that for any two orthonormal bases, VI, INS, WI, INT, of, well, H1 and H2, and every U and H, we have the sum over all elements S, sum over all elements in T. Now the inner product of L, VI, WJ, and U squared smaller than or equal to D U squared. So what is this saying? It's saying if we sort of take a formal basis consisting of VI and WJ for any IJ and S cross T, then we want the map that firstly applies L and then takes the inner product with whatever we are plugging in, that this thing somehow is bounded. But notice that this means much more than sort of this is bounded if we vary this thing and it's bounded if we vary this thing. No, we have to sum over all elements, over all combinations of elements. Yeah, I guess the prime example for Hilbert-Schmidt operators in general. Yeah, so this doesn't really look a lot like Hilbert-Schmidt, but generally Hilbert-Schmidt operators are given by sort of integration kernels. So Hilbert-Schmidt operators on L2 of some measure space are given by, let's not say measure space, let's say Rn. By, well, we send F to the map that sends x to the integral of kxy f of y dy. So we are integrating with some kernel, and then this is an operator where, and this is the Hilbert-Schmidt condition, well, k is L2, meaning that the integral of the integral kxy squared dx dy, this thing is finite. And now I guess weakly Hilbert-Schmidt on L2 and L2 sort of means the same, but where K well, now we are sending f and g, two functions on R2, to the integral of kx, y, f of x, g of y, dx, dy, where K is again an L2 map, but an L2 map, so this is on Rn, Rn, on Rn, that maps to our Hilbert space H. So again, something with an integration, something with a kernel that is an L2, but somehow different.
Why is it weaker or stronger? That's what I don't understand.
Generally, this characterization of no, we don't want the, I don't know, it looks a bit like some definition for weak continuity. I'm not sure if they are strongly Hilbert-Schmidt bilinear maps. Yeah, what are examples? So let H be some Hilbert space. And if we pick an orthonormal basis, then the identity map is trace class and Hilbert-Schmidt if and only if H is finite dimensional. Second thing, if we pick SSN, then we can define the operator TU. So if we have a countable basis, then we can define this operator by sending basically xi to 1 over n times xi. So I'm writing this as this operator, but it's just xi is sent to 1 over n times xi, meaning that this is an operator which has 1 over n as eigenvalues for every n, for every natural number n. Then T is Hilbert-Schmidt, but not trace class. Reason being that if we take the inner product of T with itself, then it is just the square sum of the eigenvalues, which is the sum of 1 over n squared, which we know to be finite. But the trace of T itself would be just the sum of 1 over n, which is infinite. Yeah, and I guess now for the more prototypical example.
Can you go back to the trace class definition just for a second?
Here.
Okay, that's fine. Yeah.
So the trace is just the sum of the eigenvalues, as always. So the fun thing is that we now already have tensor products, so we can just look at, well, let H1 and H2 be Hilbert spaces. Let's find bases. xi orthonormal bases, yi let u h1, h2, then the one time you will actually see me write out that definition, xi tensor yj u. So what is this thing? Well, by Bessel inequality, oh sorry, by Parsifal equation, Bessel inequality, whatever, this thing is just equal to u squared, meaning we can choose ds1, showing that the map that maps h1 cross h2 into h1 tensor h2, this thing is weakly Hilbert-Schmidt. Just because this thing here is equal to the square of, no, I'm not doing that. Well, you can write u in terms of elementary tensors and then write it all out in one ugly beast of a sum. But ultimately it will just turn out to equal that thing here. So
basically this is somewhat equivalent to saying that the overlap is going to be maximum with itself, right?
Well, it just means that we can calculate the norm squared by taking the sum, which, I mean, it's the same as in any kind of Hilbert space. You always have u squared is equal to the sum of that thing for a basis, for an orthonormal basis vi.
Yeah.
So yeah, I mean, this equality already shows us that this map up to bilinearity is very likely, again, such a thing that has this universal property. So no, I'm not there yet, actually. Next thing, which, oof, no, I'm not doing that. Sorry. Well, basically, I don't know if I need this, no or not. So so I was also going to bring this example of L2 spaces, of like measure spaces, and then you can do some Houdini magic and somehow this also works. But I'm just going to state it as a fait accompli and not you should actually care. This is what we are doing in physics all the time. But I guess we will see it when we get there. So yeah, I guess what I'm trying to say is from this last example, we see that example 2 fully characterizes the tensor product of two Hilbert spaces, because the universal property for Hilbert spaces is as follows. For any weakly Hilbert-Schmidt form, not form, map, L going from H1, H2 to H, where H is any Hilbert space. There is a unique bounded map such that, well, this triangle commutes. So again, we managed to characterize, we again managed to characterize the tensor product of two vector spaces, in this case, two Hilbert spaces, via a universal property involving bilinear maps. But since we usually want boundedness, we have to require an appropriate condition for our bilinear map, and that condition is that that map happened to be weakly Hilbert-Schmidt. And I guess from this, we can also more or less see, or I guess from this plus what we've done before, that if ui, ins, vj, j, and t are orthonormal bases of h1 and h2, then ui tensor vj, ins, j, and t is an orthonormal basis of h1 tensor h2. So in particular, if they are both separable, then the tensor product is also separable. Important lemma. What does this say about spaces we actually care about? What does this say about L2 spaces? Let S1, sigma 1, mu 1, and S2, sigma 2, mu 2 be, okay, that was the condition, be separable measure spaces, meaning that sigma 1 and sigma 2 are generated by countably many sets. Then L2 space on S1 cross S2 is isomorphic to the tensor product of one L2 space with the other. Proof is not very hard. What does that mean? Well, example, S1 is equal to S2 is equal to R3. Then we have that or in other words, we have the Hilbert space that describes one quantum particle. We have the Hilbert space that describes another quantum particle. And the Hilbert space that describes both of them is given by a wave function that takes two position coordinates. In physics, we've always taken this to be self-evident, but there's still somewhat of a stretch between saying that the tensor product of the two Hilbert spaces describes the system composed of both particles, and actually saying that, well, yeah, then a wave function is just given by a function of two positions. Yeah, what was my remark? Yeah, that's when that's why when we're doing multiple particle systems in physics, we can treat multiple particle wave functions just as functions of multiple variables. And yeah, I guess next thing if we tensor an L2 space with something else, then that is the same as the L2 space of function that map to that other space. Again, something that shouldn't really surprise physicists. I guess in particular, I had what? Okay. In particular, if we have a particle that has some extra structure, for example, a spinor system instead of a scalar system. So we have some extra Hilbert space here, something like C2 for spinors, or C4 or something. And then this second tensor power is just, well, by this thing here again, the same as functions defined on a product of two spaces, but now mapping to the tensor product of those two things, meaning that if we have two spinors, we need not like 2 or 4 coordinates, but 4 or 16. So I guess that is spinor indices. Not that I would know much about that. And now we can again construct tensor algebras. I mean, we also have direct sums here. They are a bit more difficult, I guess, but you can still define them, do the same constructions as before. So we define the 0th tensor power to be C, and the nth tensor power to just be H tensored with H to the n minus first tensor power. Then define the tensor algebra of H to be the direct sum of the tensor powers. And well, then we can again define that thing, symmetric power for the symmetric algebra of H to be the tensor algebra divided by, well, that same ideal, except that now it's a closed ideal in a Banach algebra, I suppose. And we can also define the exterior algebra. And now the big question, what do we call those two algebras? Say it with me, Fock space. Well, bosonic and fermionic. Fock space, of course. So, fun little question. What does this look like for our favorite example of a Hilbert space?
Is there a Clifford equivalent to?
I mean, sure.
Like, is it
Not
special?
sure
Like, is it
would be
special
that
or
much
is it
fun.
like,
Sorry, what?
is there anything special about it or not?
No, I mean, you can define it the same way. I just don't know why it would be useful or why it is useful, but
Okay.
probably it is. I don't know. What does it look like for H is equal to L2S? And I mean, we have shown that L2 sort of converts tensor powers here. That L2 sort of converts products into tensor products if you pull them out. So in particular, it converts tensor products into just normal products. And yeah, I guess also fun fact, if you have two spaces, I don't know, S and T, take their disjoint union, then L2 of that is just the direct sum of those two things. Sorry, L2. Just because you give a function, you give an L2 function on a disjoint union by giving an L2 function on one part and an L2 function on the other part. And as long as things are finite, it just works. But I mean, if we're doing, sorry, not finite, but like convergent, so we shouldn't have any trouble also applying like infinite direct sums to that. So the tensor algebra of H is then just L2 of H. Well, that thing, essentially. Take the disjoint union of all powers of S, and I suppose S to the 0th is just a point, meaning that an element of the tensor algebra would be given by an L2 function that takes arbitrary, it takes an arbitrary amount, an arbitrary number of coordinates, and spits out a complex number. And well, what is SH then? Well, that's the functions that do the same thing, but that are symmetric. And the alternating algebra would be functions on the same space that are alternating, or I guess anti-symmetric. Which, I mean, again, lends credence to the statement that a fermionic wave function is anti-symmetric and a bosonic wave function is symmetric in its coordinates. And just in time, that was the lecture.